So today we are in 3.2 and we are going to talk about a new word, but it's something that we've actually have been looking at before. We're just now going to call it by its official name. So today we're going to start talking about limits, and we're going to start with graphical and numerical evaluation of limits. So what is a limit, first of all? Okay, so when I look at f here, I have x squared plus x minus 2 over x minus 1. I know, because we've talked a lot about domain restrictions, that x cannot be 1, right? So my domain restriction here is that x cannot be 1. But what a limit does is say, okay, well, right, 1 will be an interesting place. What is going to happen around the graph at 1? I know I can't put in 1, but what happens around 1? So that's what a limit is what is happening with my function as I get really super close to 1 on either side of 1, meaning to the right of 1, like 1.001, and to the left of 1.999. Okay, so we're going to first look at a table. Okay, so this is actually, I have f already defined here. This is f is our function here, which is x squared plus x minus 1. And this is kind of nice that Desmos will allow me to make this table. So let me see, maybe I can move this up a little bit better so you can see it a little bit better. So f is defined as our function there, which is x squared plus x minus 2 over x minus 1. And what I'm doing with this table is I'm actually putting in values on both sides of, you see the 1 there in the middle. And so when I approach 1 from the right, that's the first part, it's numbers slightly to the right of 1, which was 1.1, 1.01, and 1.001, then my y values here are 3.1, 3.01, and 3.001. So if I approach then from the left, which means for numbers smaller than 1, the left-hand side of my number line, 0.9 is the furthest away, which is 2.9. I approach a little closer, and what the point is basically I'm getting a little closer with my x. My y value is just barely changing, right? It's holding fast. So basically what is happening here is at 1 is that from the right-hand side, my numbers are just ever so slightly bigger than 3. From the left-hand side, they're ever so slightly smaller than 3. And so in this case, we're going to say that our limit, that's the answer to our question here, the limit as x approaches 1 of f is in fact 3. Okay. Now this is really an estimate that we're doing at this point. This isn't really, but this is a good way to introduce limits. So I want us to look at the graph of f here as well. Let me put this on here. And essentially, you notice my graph looks continuous, right? So this is, again, a drawback of graphing software is that we'll fill in spaces for you. So at 1, but it does look like my graph, what I'm thinking is from the right and the left, it seems to be approaching the same value. Okay, so basically I should see then at x is 1, let me see if I can put a point on my line here. When x is 1, no, it doesn't want to let me. There we go. So as x approaches 1, see that little undefined space, it pops up there? Okay, so at 1 it's undefined, but my graph seems to, when I take my finger off of it, the hole just fills itself in. But when I take my finger off, or when I look at it up close, when I look really close, it's undefined there, but my graph looks like it's filled in. Okay, so, but my graph is still approaching the y value there. Like if you notice, let me see if I can do it again here. That when I get around 1, right, see how my y values there are 2.9. I get closer, it was flashed up 2.97 for a second. And when I'm just to the right of it, the y value is approximately just a little bit smaller and a little bit larger than 3, depending upon which way I'm looking at it. So it doesn't matter if f of 1, right, is defined or not. When I'm talking about a limit, I'm actually not talking about what's going on there at the point, because usually the point of looking at the limit in the first place is because we know there's something going on weird at that point. So we look at the limit because we want to know how the graph is behaving right around that point. not what it's doing actually at that point. Okay, so let's look at another one. So we have g here, which g of x is equal to x over the square root of x plus 4 minus 2. So this one maybe isn't quite as obvious, but the problem with my domain restriction, well, one, it's got to be larger than -4, which is one thing, but then a 0 would be at x equals 0. Because when x equals 0 here, I'm going to get the square root of 4 minus 2, which gives me 0 in the denominator. So I want to look at the limit as x approaches 0, right? Because that's where I know that odd things are going to happen. And so I'm wondering, okay, what is going to happen? All right, so let's look at the next graph that I have here. All right, so there I have g defined. And again, I'm going to show you something about the graph here in a second, but g of 0, it says it's undefined, and when I look at the table, around 0, 0 is right in the middle. So from these values are to the right, so it's the limit as x approaches 0 from the right, are slightly bigger than 4. When I go on the left-hand side of 0, I see that my values are, as I get closer to 0 on each side, right, I'm starting with the furthest points at the top and the bottom, and then they get closer in the middle. Then I'm almost to 4, I'm slightly above 4, so we would say, this is just a guess, right, is really what we're doing, but it looks very close to 4. So we're going to write here that this is equal to 4. Now again, I'm going to show you a flaw in this graph when I go to graph it. All right, so this time I'm going to check the box. And I'm going to graph this. Okay, so you see how at 0, it appears that my graph is in fact, right, there's the x-axis, at y equals 4. And from both sides my graph is approaching it. Now actually, maybe it won't do it, it was doing it earlier. I was actually finding that when I got to the 4, or the 0 here, it actually showed it as being 4. It's not 4 because when I plug in 0, I'm dividing by 0. Is it going to do it for me here? Ah, no, this time it's showing me undefined. But the first time I put it in, it was actually showing that it was in fact 4 there. So be careful, beware of your graphs. It doesn't show you those little undefined spaces until you zoom in on them. And sometimes even then it can mess it up a little bit. So again, I want to say it doesn't matter what f of or g of 0 is undefined. It just matters that the graph appears to be approaching the same y value. That's the important part. All right, so let's look at this value down here. Now this time I have h of x equals x over x minus 1 squared. All right, so let's go to my next graph here, or I'm going to go to my table first. Okay, there we go. I want that to go away. Why don't we make that go away? There we go. Okay. All right, so here's my next table, and this is h again. So at 1, right, that's where I'm worried about my denominator being 0. That's where we're looking. That's why we look at limits in the first place for the most part. There are places that we look at that are continuous, but those are more for an exercise. Okay, so I'm going to look for the limit as x approaches 1 because that's my domain restriction. So I want to know how my graph is behaving around that domain restriction. Well, of course, I didn't take the other graph off, so let me come back here and uncheck that box. I don't want the purple graph showing anymore. We'll come down here and look at this table. So now I'm going to approach 1 from either side. So it's in the middle there. So there's my table. Now what I notice this time is that the 1 is undefined in the middle. As I get slightly bigger, look, and when I start down here, it's at 110, and I'm only increasing, right, I'm just a little tiny bit, right? If you look at 1.1 and 1.01 on a number line, there's hardly any difference between them, but look at what happened to my y values. They jumped, right? I went from 110 to 10,100. right? And then up here, I've got even more zeros. That's just in scientific notation because it doesn't have enough room. But that means move that decimal place 6 places to the right. And so I'm going to have even a couple of more zeros after that. So it's even a bigger number. So that means that as I'm approaching 1 from the right-hand side, my y values are just growing and growing and growing. And every time I put in another 0, my y values are going to jump even more. So we say that that's like infinite behavior, right? That as x gets closer and closer to 1, my y value is growing and growing and growing really, really fast. And as I approach it from the other side, it does the same thing. So as I approach from 0.9, right, it's at 90, I add 0.99, so I'm only going up 100th, and my y value is jumping to 9,900, and so forth. So it's growing in both directions really large. So the way that we write this, that means essentially this is our first limit that fails to exist. So here, my graphs are approaching the same number. When my graphs don't approach a specific number, then we say that the limit does not exist. Now, in a lot of cases, what we do when we say the limit doesn't exist is, well, the reason why we looked there in the first place was because we wanted to know what the graph was doing. So we can actually say, because if you noticed on those, my y value in both cases was approaching infinity in both directions. That doesn't always happen. Sometimes when I look at it from the left-hand side, it goes to infinity, and sometimes it goes in the really opposite negative direction as well. So we would say that this would graph, even though it doesn't exist, we would say that since the y values as I approached 1 from the right, let me write it this way. So the limit as x approaches 1 from the right of h, all my y values got really big. So I say that's infinity. And all of my y values as I approached 1 from the left also got really big. We say that's infinity. So we can write it like this, that the limit as, this is the way we say we're looking at the right hand and the left hand limit with this notation, okay? So it's infinity. So we could actually say that it doesn't exist, but it's equal to infinity because both of these match. It doesn't exist unless it approaches a specific number. Okay, so let's look at another interesting example. So this is y equals the absolute value of x over x. And so we'll go to our table here. Now this is a really interesting one. So look at my table here. And so when I get really close, when I go on the negative side, okay, when I have just slightly smaller, this is approaching from the left of 0, all my y values end up being -1. And you can kind of see, like if I just plug in values that are negative, let's say I plug in -5, right? I'm going to get the absolute value of -5, which is 5, divided by -5. I'm going to get -1, right? If I put in a -4, I'm also going to get out -1. So as long as I'm using negative x values, I'm going to get out -1. So let's write the way that that looks. We would say that the limit as x approaches 0 from the left of, we'll just use the absolute value of x, right? What goes in here has to be either the name of the function or the function itself is equal to -1. So let's look in the opposite direction then. The limit as x approaches 0 from the right of the absolute value of x over x. This is equal to, maybe you saw, right? When I use positive values, all my y values are 1, right? And that's, if I just plop in a couple numbers that are positive, if I use +5 this time, I get 5 over 5, which is 1. If I use 4, I get 4 over 4, which is 1. And so this graph, actually, maybe I'm just really struggling with this. All right, it looks like this. Very interesting, right? So this one, and these are open, you can't really tell again, these are open circles attaching me at 0 because 0 is not part of my domain. And so here we have a situation where like the right and the left hand limits go to a number, like the previous example, right? My numbers just kept getting bigger and bigger and bigger. These are always going to be -1 and 1. It's just that the overall limit fails to exist, right? We're going to say that this does not exist. My DNE for short does not exist because the right, this is the right, and the left-hand limits don't agree, right? They both, from each side, they approach a specific number. They just don't approach the same number from both sides. So this one fails to exist because we have that jumping behavior in there, right? That's like I'm coming up here to the y-axis and all of a sudden my graph just goes bloop and jumps up and now it's up here, okay? All right, so one more example that I wanted to do, and this is an example of a piecewise function, and I just have it graphed here. So my graph here is f of x is equal to 3 as long as x doesn't equal 2, and at 2 it's equal to 0. So this is like y equals 3. It's this horizontal line here at y equals 3, and it's not defined here at x equals 2. So that means I'm going to have this hole. Now I put the hole there so that we could see it because my graph would just fill it in if I used Desmos. And now the 0 means at 2, my y value is 0. So this is what my graph looks like. Okay, so what I want to look at is, right, my right and left hand behavior. So I really want to emphasize something here. So when I approach 2, so I'm looking at the limit as x approaches 2. So I'm going to write out the right and left hand. This is one way to do it. So when I approach 2 from the right, so that means I'm going to look at my graph. Here's the right of my 2. So I'm going to look here and I'm going, okay, as I come here and look, what is my graph doing here at when I get really close to 2? Well, it looks like it's approaching the y value of 3, right? It's right there. And then I'm going to look at coming from the opposite direction, 2 from the left. That means I'm going to choose a spot over here and approach from. And as I get really close, right, I'm also approaching this y value here, which is 3. So the limit does in fact exist. It's 3 because both the right and the left-hand side of my graph are approaching the same y value. But I'm trying to emphasize again, right, when I look at f of 2 is 0, right? It's down here. And so the existence of this limit, I can't say it enough time, has no bearing upon what is happening right there at 2. It doesn't matter if that point is filled in. It doesn't matter if it's down here. It doesn't matter if it doesn't exist. When I'm asking about the limit, I'm asking about the graph right around that value, not the actual value, right? If I wanted to know what f of 2 is, I'd just ask, and f of 2 is 0. Instead, I said, what's the limit as x approaches 2? Okay, so let's look at the informal definition of a limit here. Okay, so an informal definition of the limit basically says that if f becomes arbitrarily close, it means as close as I want to get to a single number L as x approaches c from either side, then we say, in English, we say that the limit as x approaches c is L. And then the math form of that is the limit as x approaches c of f is L. Right? So basically, as I get really, really, really close to some value here, then my y value keeps getting really, really, really close to this value here. Okay? And if it doesn't approach a specific number, then that limit does not exist. Okay? So in a lot of them, most of the examples we did, the f of c did not exist since c was not part of the domain. Again, so the existence of a limit is not dependent on whether f of c exists. So whether f of c is there or somewhere else or fails to exist, it doesn't matter. We're looking at the graph around it, not that place specifically.